Hello everyone, my name is Pedro, PhD student at RITMO. I'm going to present this topic, sonic exploration for 3D Swarmalators. So, what are the Swarmalators? Well, the Swarmalators, they are oscillators whose phase dynamics and spatial dynamics are coupled. So you can imagine an object, for example, and this object internally has an oscillator or some internal states, and this object can move in space and can work in its state. So basically, you can think about in many of these objects that are related with each other in a kind of swarm. So the thing is that because this is a swarm of these objects, this swarmalator takes the name from that. It's a swarm plus oscillators that works internally. So basically, the movement of these objects and also the phase of these oscillators depend of the position and also the phase of the other agents. So this Swarmalator model can be found in this paper here, oscillators that syn and swarm. So this is the general model. So basically what we have here is delta position and a delta phase. So a change in position and a change in phase. As you can see here, for a specific agent I, the change in position depends from both the position and the phase of the other agent. So this is a contribution of all the agents for this change in position as well as the change in phase. So an instance of this generic model is this other model that is inspired in the Kyrre model for coupled oscillators. So basically, we are reduced this to just the tweaking these two parameters, J and K. So J is the extent to which the phase similarity enhances spatial attraction. So this parameter J allows to see or to model how these agents, the set of agents can be closer or far from each other. And the K is the phase coupling strength. So how fast we can reach some kind of phase state like synchronization or any other kind of behavior. So if we manipulate these two parameters, J and K, we can have different specific patterns. If you think about that the phase is related with a specific color, we can say that if all of the agents in this group of Swarmalators are synchronized, all will be with the same color. So as in this case, if you can see, there are a lot of these objects, and this state is called the static syn if we have these two values of J and K, 0.1 and 1. It's a static because the agents are not moving, so they are just synchronized in phase. By the other hand, we have this other state in which all of them are static also, but they are unsynchronized, so the phase are different. Also, depending of other values, we can have several nice patterns. For example, we have these patterns in which all the agents are static, but there is, you will see that later in a demo, we have a wave, a phase wave that is going around. So that means that all the agents are changing the phase in time. Also, we can have this kind of clusters of phases in which the phases are separated in these patterns. And finally, this other pattern is when now the agents are moving around, and apart from that, they are changing in phase. So the thing that I want you to understand is like the movement and the phase depend of position and phase from the other ones. That's the key thing here. So now the thing that I'm exploring is how can we map some parameters from these Swarmalators of this set of objects to generate sound. So we have to design a kind of mapping strategy for doing that. So I'm going to present two of them today because we have several or many, almost infinity options to do this. One of these is mapping with a melody or pitch sounds. So basically what I'm using is the two main properties like phase and position from a Swarmalator. The phase, I'm taking the phase like as it is, but for the dynamics of the spatial parameter, I'm taking this angle that is basically the angle between the center of all the agents that are here, of this right vector regarding the vector from the center to a specific agent I. So as you can see here, we can have different angles depending of the location of the agents. And that is the parameter that I'm using here. So the phase I'm mapping with a frequency. It is direct, like in a range of values, or in discrete values, like in a musical scale. So this will be the frequency for a sine oscillator. This angle, I'm mapping with the phase of a low frequency oscillator, the amplitude, so that I can modulate this sound oscillator in amplitude with this parameter. Yeah, that is one. The other one is something that you will see that is a little bit more logical to the purpose of the Swarmalators. I'm using the phase for actually the phase of when you are playing a hit sound. So this is basically the delay in which you can play the sound. Also, I'm using the phase just for giving a little bit of differences in the dynamic for the hit sound. I'm manipulating a little bit the pitch of the hit. So I generated this hit sound. Apart from that, I'm using this for triggering rhythm patterns, specifically Euclidean rhythm patterns. So you will see or you will hear that it's not just a hit, but it's a trigger for a specific pattern, a set of events in time. Yeah, okay, so I'm gonna show you in real time the demo. So yeah. Okay, so this is a simulation of the Swarmalators in a 3D space. We have now 3 that are unsynchronized, so we can actually add more of them. So in this specific pattern, we have full synchronization, as you can see. Yeah. So if I put the state of the phase wave, moving phase wave, it will be like something like this. Yeah, as you can see, it's a kind of nice pattern in which you have several of these elements that are going around, and you can notice that there is a kind of wave that's going around. So how it sounds? For the range of frequency, it sounds like this. Yeah. So I can change the state of this, for example, to something more static. This is the static phase wave. Or synchronized. And they are synchronized. So if I add more of these agents, they are randomly assigned a random position and also a random phase. So they are going to be influenced by the other ones, and they are going to synchronize. Yeah. But what if I map this with something more, let's say, more pleasant? And for example, I'm mapping not this to a specific range of frequency, but I'm mapping this with a frequency from a musical scale. So I can change that. And then I can provide some movement to the sound. So this is one of the examples that we can map this thing nicely with sounds. But what if we use the hits pattern? So if everything is synchronized, as you can see, it's like everything is in sync. And then I can change this. Yeah. And what if I use some patterns? So now this is not just triggering one sound, but it's triggering a set of sounds, set of patterns. So I can play with this and have these changes in dynamics regarding the sound. Also, Apart from this, I add something else. Like we can have, for example, manual objects that we can manipulate, and we can have some kind of interaction. In this case, this is, let's say, a manual Swarmalator. This is not influenced by the other ones, but the other ones are influenced by this one. So if I want to synchronize, for instance, I synchronize everything, eventually, because this is not influenced by the other ones, they will take the same phase of this one. If I change the phase, for example, to this color, and they're going to follow. Even like if I move this in a space, they are influenced by this. And if I add other randomly, sorry, yeah, we can have like a kind of, I would suppose, averaging the phase of all of these manual, because they are not coupling with the other ones. Yeah. So this is a way in which we can interact with this one. So imagine these cubes that could be a human, performer that is interacting with these agents. So yeah. Okay. So in conclusion. Yeah, okay, you can see that we have mappings that could be aesthetically appealing, but that depends, it's subjective. We can experiment with this Swarmalator. It's useful for automatic synchronization. And we have several possibilities for human interaction. And of course, it can be applied to other fields. Because you are working with the concept of entrainment, you can use this for your research. So the idea of this is like trying to use this for implementing human SOAR interactive music systems in my PhD project, and exploring other kind of mappings, and try to work with decentralized objects, and maybe scale this to other physical agents like robots or things like that. Yeah. Any question?
Thank you so much, Pedro. That was amazing. And so cool to see it in real time and how you can actually use it and play music with it. For those of you that can't see, there's actually a keyboard up here, and he was playing on the MIDI keyboard. So I'm going to show that. Yeah, amazing. Are there any questions? Oh, wonderful.
That was very nice. Thanks very much. I was just wondering if you've experimented with the decision as to what Euclidean rhythm the rhythm section will use. You know, have you set various different relationships between the conditions and the choice of Euclidean rhythm?
Sorry, can you repeat it? The last
How do you decide which Euclidean rhythm to use when there's a multiple?
Oh, yeah. Okay. No, actually, this is like random patterns that are generated every time one of these sound agent is generated. So the thing is that they are distributed in one specific range of time, and then there is a Euclidean rhythm generator. So it randomly generates a pattern depending on some specific parameters. So if you start again the program, you will have a different pattern. So I'm not actually deciding per se. I have some parameters, and then it generates randomly. But still, because it's within the frame of an Euclidean rhythm, that's why it sounds like something that makes sense, I would say. Yeah.
Thanks for this really cool presentation.
Thank you.
I have a question about mapping to sound. The phase, and you talked about phase and angle.
Yeah.
Phase, and so the phase isn't the phase also kind of the sign of angle. So is they're kind of the same thing, but in the circular plane?
No.
Or is
yeah,
it the...
because, yeah, maybe it's not clear here, but yeah, remember this. There is two parts, like the oscillator and the object, the dynamics of the object, the spatial dynamics, like the position. So the phase is the phase of the oscillator.
Okay.
Yeah, so you can separate that, the oscillator and the position of the thing. So the phase is the phase of the oscillator, and this angle is a spatial angle. Like you have the object, and you calculate the center, and you have the angle between this vector and this. So this is a spatial parameter.
Okay.
So the two are different. Yeah.
Yeah, I thought it's just the same oscillator and the unit circle.
Yeah.
Okay,
No, they're
thank you.
separate. Yeah. Okay. Very cool.
Thank you. I just checked the YouTube chat. There were no questions. But I was wondering, like, what is your vision for the next step, Pedro? What, like, when you've finished your PhD, what's like, are you planning an installation, like 3D sound? Like, how will you apply this that will in your PhD in the future?
Yeah, basically, I'm exploring this for the synchronization part of my PhD because my PhD is related with human sound interactive music systems. So basically, you can have several levels of this. I will target to the level in which you can make music with artificial entities. So if you can have something congruent, you need a strategy for synchronizing rhythm, synchronizing music, and everything sounds, let's say, nicely. And so yeah, I'm exploring Swarmalators so that I can have a tool to manage and approach this synchronization in this kind of system. Yeah.
Amazing. Thank you so much. Thank you again to Pedro.
Thank you.